Hello there, and welcome to Sleepy Science Vault. Somewhere in the fabric of space and time, there may exist structures so strange, so quietly radical, that they challenge everything we think we understand about the universe we live in. Not black holes. Not stars. Not galaxies spinning slowly in the dark. Something else entirely. A wormhole. The name itself sounds almost too simple for what it describes. And yet, the concept has occupied the minds of physicists for nearly a century, not as science fiction, not as fantasy, but as a genuine, mathematically consistent possibility written directly into the equations that govern the cosmos. So what exactly is a wormhole? At its most fundamental level, a wormhole is a connection. A passage. Imagine two separate points in the universe, two regions of space that might be separated by billions of light years, or perhaps by the full breadth of the cosmos itself. Now imagine a bridge between them. Not a bridge you could see from the outside, not a tunnel carved through the space between. Something far stranger. A shortcut that doesn't travel through the space in between at all, but rather bends space itself so that two distant places are, somehow, touching. A wormhole has two mouths. Two openings. And connecting them is what physicists call a throat, a region of intensely warped spacetime that links one mouth to the other. You enter through one mouth, you pass through the throat, and you emerge from the other. The two ends might be in the same galaxy or on opposite sides of the observable universe. From the outside, they appear as two distinct locations. But through the throat, they are one. This alone is enough to slow the mind down a little. To make you pause and reconsider what the word connected even means. Because what a wormhole describes is not simply a path through space, it describes a different kind of geometry. A spacetime that is folded, not flat. A universe that is, at its deepest level, more interconnected than it appears. The reason wormholes are even possible, at least on paper, comes down to the nature of spacetime itself. According to Einstein's general theory of relativity, space and time are not fixed, rigid things. They are dynamic. They bend. They curve. They respond to the presence of mass and energy the way a stretched fabric responds to weight placed upon it. A massive object warps the geometry around it, and everything that moves nearby follows those curves, including light, including time itself. A wormhole takes this principle to its absolute extreme. The curvature involved isn't subtle. It isn't the gentle curve that keeps planets in orbit or bends starlight around the sun. It is extreme spacetime curvature. The kind of warping so severe, so profound, that it doesn't merely deflect a path, it folds the map entirely. Two places that had no business being near each other suddenly share a geometry. Suddenly touch. And here is where things become quietly wonderful. Because you might imagine a wormhole as a tunnel, a long, cylindrical passage with walls, like a tube running through space. That image is natural. It's how the word wormhole tends to make us picture things. But that picture is misleading in a beautiful way. There are no walls. Inside a wormhole, there is no interior surface to press your hand against, no ceiling overhead, no floor beneath you. What exists instead is something harder to visualize and far more interesting: warped paths. Curved geometry. Space itself bending in such a way that your trajectory leads you from one region to another without any solid structure guiding you. The throat of a wormhole is not a place you are enclosed within. It is a shape that the space itself takes, and you simply follow. Locally, from the perspective of someone moving through it, the interior of a wormhole might not look like a tunnel at all. There's no flashing light at the end, no obvious visual indicator that you have passed through a throat in space-time. The experience, in some theoretical models, might feel almost ordinary, like moving through open space, with perhaps a strange distortion in the view around you, a lensing of distant stars. The strangeness is in the mathematics, not necessarily in the view. This points to something remarkable about how physicists actually think about wormholes. They are defined not by their appearance, but by their topology. Topology is the branch of mathematics concerned not with distances or angles, but with the fundamental shape of things, the way surfaces and spaces are connected. A sphere and a cube are topologically the same. A donut and a coffee mug are topologically the same. But a simple flat surface and a surface with a hole through it are topologically different, and no amount of stretching or bending can turn one into the other without tearing. A wormhole represents what mathematicians call a multiply-connected spacetime, a geometry in which the fabric of space contains loops, passages, connections that a simple, ordinary universe does not. In ordinary, simply connected space, there is essentially only one way to travel between any 2 points, the most direct path through the open expanse. In multiply-connected space, there are multiple paths. Alternative routes. Topological shortcuts built into the very structure of reality. And the throat of a wormhole is defined by what are called topological invariants, mathematical quantities that capture the essential nature of that connection and remain unchanged even as the geometry around them shifts and flexes. These invariants are what make a wormhole. They are the signature of that passage, encoded not in how it looks, but in what it fundamentally is. There is something quietly philosophical about that. The wormhole's identity is not a matter of appearances. It is a matter of deep structure. Of what remains true about it no matter how you look at it, no matter what angle you approach from. One of the most disorienting things physicists have discovered in studying wormhole geometry is that there is no clean boundary between the inside and the outside. In everyday experience, we take for granted that we can always tell where we are, inside a building or outside it, inside a room or in the hallway. But with a wormhole, that distinction dissolves. There is no local test you can perform, no measurement you can take at any single point, that will tell you definitively whether you are inside the throat or outside it. The geometry transitions in a way that has no sharp edge, no clear moment of crossing. This is not a limitation of our instruments. It is a feature of the mathematics itself. And it deepens as you explore further. The length of a wormhole's interior, the distance you would travel while moving through the throat, has, in many theoretical models, essentially nothing to do with the spatial distance between its two mouths. The throat could be meters long while the mouths are light years apart. Or the throat could be vast and winding while the two mouths sit, in ordinary space, quite close to one another. The interior length is its own quantity, governed by the internal geometry of the throat, not by anything measured from outside. This is the kind of fact that, if you sit with it quietly for a moment, begins to feel genuinely vertiginous. Because it means that space, in this framework, is not simply an empty container with fixed dimensions. It is something richer. Something that can contain more geometry than its exterior appearance suggests. Something that can hold, within a small region, a path far longer, or far shorter, than the surrounding universe would imply. And that same quality extends to volume. There is no single, well-defined volume that the interior of a wormhole possesses. The concept of how much space is inside breaks down in the same way that the concept of inside versus outside broke down. The geometry is too strange, too topologically complex, for such familiar measurements to hold clean meaning. We are left, in the end, with something that is not a tube, not a tunnel, not a door in any ordinary sense. A wormhole is a feature of the shape of the universe, a knot in its geometry, a quiet impossibility sitting at the intersection of mathematics and physical reality, waiting, perhaps, to be found. Long before you reach the throat, the universe around you begins to change. It starts subtly. A slight distortion in the arrangement of stars. A bending of light that doesn't quite match what you'd expect from any ordinary object in space. You might notice it first at the edges of your field of view, distant galaxies shifting position, arcing gently, as though the space between you and them is no longer behaving the way space is supposed to behave. And you would be right. Light, as it approaches a wormhole's mouth, does not travel in straight lines. It follows the curves of spacetime, and near a wormhole, those curves are profound. The result is a kind of optical distortion that physicists call gravitational lensing, but taken to an extreme that no ordinary massive object produces. Stars that should be behind the wormhole appear beside it. Entire regions of the distant universe seem to fold into view around the edges of this invisible structure. The sky, near a wormhole entrance, becomes a living map of distorted geometry, beautiful, deeply strange, and deeply informative to anyone who knows how to read it. What you would see, in the most striking sense, is something almost impossible to reconcile with everyday experience. You would appear to see through it. Not through it the way you see through glass, with a clear and undistorted view of what lies beyond. But through it in the sense that light from the far side of the wormhole, from the region connected to the other mouth, perhaps light years away, would be threading its way through the throat and arriving at your eyes. The wormhole would appear, in some theoretical models, almost like a window. A sphere of alien sky, hanging in space, showing you a view from somewhere else entirely. Stars you have never seen from this position. A completely different patch of the universe, framed within the mouth of the wormhole like a painting of somewhere else. This is one of the most haunting visual properties that theorists have described. The wormhole doesn't just connect two places, it allows them, in a sense, to see each other. To be luminously aware of each other across the vast architecture of space. And yet, for all that visual strangeness, something crucial is missing from what you can observe at this stage. You cannot see where you're going. There is no signal, no beam of light, no information arriving from the exit mouth that would allow you to know what is on the other side before you enter. The geometry of a wormhole's throat is such that until you are inside, until you have crossed into that warped interior region, the far end remains, in a meaningful sense, unreachable by light traveling toward you from outside. The throat does not broadcast. It does not announce what waits beyond. This is not a matter of limited technology. It is a structural feature of the geometry itself. And that silence from the far end is one of the first hints that a wormhole and a black hole have more in common than their outward appearances might suggest. As you draw closer to the throat, the distortions around you intensify. The lensing becomes stronger. The apparent window of distant sky grows larger, brighter, more overwhelming in your visual field. And here, at some critical proximity, something else becomes apparent, or rather, something becomes unresolvable. There is no local way to tell whether you are approaching a wormhole or a black hole. From the outside, the gravitational signatures can be virtually identical. Both warp spacetime profoundly. Both bend light dramatically. Both can possess the same mass, the same external gravitational influence, the same effect on nearby objects. The distortions you see in the sky could belong to either. The equations governing your motion toward either one look, at a distance, strikingly similar. This is not a trivial observation. It carries deep implications for how we might search for wormholes in the real universe, and for how we interpret the exotic objects we observe in distant space. A wormhole, if it exists, would not announce itself with a label. It would sit there in the cosmos, geometrically quiet, waiting to be distinguished only by observations that go beyond what we can currently make. The distinction between the two only begins to reveal itself as you approach what behaves, from a certain mathematical perspective, like a horizon. In a black hole, the event horizon is a one-way boundary, cross it moving inward, and you cannot return. The geometry on the far side leads only deeper, toward the singularity. But at the throat of a traversable wormhole, the behavior is different in a way that is subtle but essential. The throat has a horizon-like quality, a surface at which the geometry reaches a kind of critical point, but it is not, in the same way, a point of no return in the same absolute sense as a black hole's event horizon. The geometry opens up again on the other side, into a new region of space rather than collapsing toward a central point. And this brings us to one of the most beautiful and disorienting ideas in all of theoretical physics. A wormhole, in the most well-studied theoretical models, does not simply connect two points in ordinary space. It connects two black hole exteriors. Two separate regions of spacetime, each of which, from the outside, looks like the space around a black hole. The wormhole's interior acts as a bridge between them, a shared space, a mutual interior, linking two geometric structures that are otherwise completely separate from the perspective of any observer staying outside. The mathematics behind this comes from one of the earliest and most profound solutions ever found to Einstein's field equations. When physicists Karl Schwarzschild and, later, Martin Kruskal and George Saccharis fully analyzed the geometry of a black hole, they discovered that the complete, maximally extended solution does not describe just a black hole surrounded by ordinary space. It describes something far richer, a geometry containing two separate external regions, two universes, or two distant parts of the same universe, connected by an interior bridge. That bridge is sometimes called the Einstein-Rosen bridge, after Albert Einstein and Nathan Rosen, who first described it in 1935. And its interior is not simply the interior of a black hole. It is a shared space, a region that belongs, mathematically, to both exteriors simultaneously. Sit with that for a moment. The interior of a wormhole, in this picture, is not owned by either side. It is a commons, a mutual space that both connected regions can claim as their own interior, approached from opposite directions, like two corridors that meet in a room neither of them fully contains. But the geometry does not stop there. Connected to this picture is something even stranger, the presence of what physicists call a white hole. Where a black hole is a region of spacetime from which nothing can escape, a white hole is its time-reversed counterpart, a region from which everything emerges, but into which nothing can fall. It is the mathematical opposite of a black hole, and it appears naturally in the fully extended wormhole geometry. The interior of a wormhole, in the complete mathematical picture, connects not just two black hole exteriors, but also contains a white hole region, a sector of spacetime from which matter and light can only flow outward. The geometry becomes a four-part structure, two exterior regions, an interior bridge, a black hole future region, and a white hole past region, all woven together into a single, consistent spacetime. This is the kind of solution that emerges when you trust the mathematics entirely and follow it wherever it leads, without insisting that it conform to ordinary experience. And there is one final quality of this interior geometry that deserves to be held quietly, because it touches something that physicists find deeply significant. The interior of a wormhole, this shared bridge between two black hole geometries, can encode something called a cosmic censorship boundary. Cosmic censorship is the name Roger Penrose gave to the idea that nature, in some fundamental sense, hides its most extreme singularities from outside observers. That the points where spacetime breaks down, where the equations produce infinities, where our understanding of physics genuinely fails, those points are always concealed behind horizons, shielded from the view of anyone in the broader universe. The interior geometry of a wormhole can carry that boundary within it. The point at which the interior ends, at which the wormhole can no longer be extended further, at which spacetime reaches its absolute limit, that point can be hidden inside the throat, inaccessible to anyone who remains outside, protected by the geometry itself. It is as though the universe has a sense of propriety about its own deepest secrets. The entrance to a wormhole, seen from a distance, is a spectacle of bent light and alien sky. It is a place where the cosmos seems to fold gently back on itself, where distant regions glow through a passage that has no walls and no announced destination. It looks, in many ways, almost inviting, a window, a door, a threshold into something genuinely unknown. But underneath that visual elegance lies geometry of extraordinary complexity. The horizon-like throat, the shared interior, the echo of black holes and white holes folded into the same solution, the hidden boundary where spacetime itself reaches its edge. Before you have even entered, the universe is already telling you something important. That this place is not simply a shortcut. It is a seam in the fabric of space itself, and what lies inside is something the mathematics has always known, and always quietly kept. The moment you cross the threshold, everything changes. Not dramatically, not all at once, but in the way that the quality of the air changes when you step from a quiet room into something vast and open. There is a shift in the geometry around you, registered not by your eyes but by something more fundamental. Your body. The space your body occupies. The difference in gravitational pull from one side of you to the other. This is tidal force, and inside a wormhole, it is one of the first physical realities to make itself known. Tidal forces arise whenever gravity is not perfectly uniform across an extended object. The side of you closer to the source of curvature is pulled slightly more strongly than the side further away. In gentle gravitational fields, this difference is negligible. But in regions of extreme spacetime curvature, the kind that defines a wormhole's throat, that difference can become significant. In some theoretical models, it becomes lethal. The gradient of gravity across a human body, or a spacecraft, or any extended object, grows strong enough to stretch it along one axis and compress it along another. Physicists call this process, with a certain dark elegance, spaghettification. Whether this happens to you depends entirely on the specific geometry of the wormhole you have entered. And this is where the mathematics begins to show just how varied the interior of a wormhole can be. Not all wormholes are built the same. The shape of the throat, its width, the rate at which it narrows and expands, the distribution of whatever exotic material or energy is threading it, these factors combine into what physicists describe through the metric. The metric is essentially the mathematical rulebook for the geometry of a given spacetime. It tells you how distances are measured, how time flows, how paths curve. And the metric of a wormhole's interior determines, fundamentally, whether passage through it would be survivable. Some theoretical wormhole geometries produce throats that are gentle, wide enough, and smoothly curved enough that tidal forces across a human-scale object remain comfortably small. These are the traversable wormholes that physicists find most interesting, the ones that serve as the basis for serious scientific speculation about travel and connection. Other geometries produce throats that are crushing, where the curvature is so intense and so sharply varying that nothing of macroscopic size could pass through intact. The mathematics permits both. Nature, if wormholes exist, would choose one or the other based on conditions we do not yet fully understand. Woven into this picture is something called the redshift function. As you move through the interior, your experience of time, of light, of energy, all of it is shaped by this function. In the same way that light climbing out of a gravitational well loses energy and shifts toward the red end of the spectrum, the geometry inside a wormhole imposes its own pattern of energy shifts on everything that moves through it. The redshift function governs how steeply the geometry warps time from point to point along the throat. In traversable models, this function is carefully constrained. It must not produce a horizon, must not create a point where time is experienced by a traveler comes to a complete stop. But within those constraints, it can vary enormously, and that variation shapes the interior experience in ways that are difficult to fully intuit from the outside. A throat with a gentle redshift function feels, in principle, almost like open space. A throat with a steep one compresses and stretches the traveler's perception of time, warps the light arriving from both ends of the journey, and creates an interior environment that feels genuinely alien in its temporal texture. One of the more quietly remarkable aspects of wormhole geometry concerns size and gravitational behavior. Smaller wormholes, in certain theoretical frameworks, behave attractively. They pull objects toward their mouths the way a mass pulls objects toward itself. Larger wormholes, by contrast, can behave repulsively. The geometry of a sufficiently large throat can push outward, creating a kind of gravitational defocusing rather than focusing. This behavior is deeply counterintuitive. We are accustomed to gravity as something that only pulls, that always draws things together. But the exotic matter or energy configurations required to hold a wormhole open can reverse this, creating regions where the gravitational effect on nearby matter points outward rather than inward. The practical implication of this, for a traveler, is that the experience of approaching a larger wormhole might involve not being drawn in, but being pushed away, requiring active effort to enter, a kind of resistance from the geometry itself, as though the wormhole is reluctant to be used. Inside the throat, another quantity begins to dominate the physics: the ratio of charge to mass. In charged wormhole solutions, and many of the most mathematically complete wormhole geometries do involve charge, the interior geometry is heavily governed by how the electric charge of the wormhole compares to its mass. This ratio shapes the curvature of the interior in a way that determines everything from the strength of tidal forces to whether the throat remains open, to how light and matter move through it. A high charge-to-mass ratio produces an interior geometry that is, in some respects, gentler, with the repulsive effect of charge partially offsetting the crushing effect of mass-generated curvature. The interior of a highly charged wormhole can, in principle, be significantly more navigable than that of a purely massive one. This is a subtle but important point. The wormhole's internal environment is not determined by a single parameter. It is the interplay of multiple physical quantities: charge, mass, the exotic energy threading the throat, the specific shape of the metric, that determines whether the interior is a corridor or a compression chamber. Geometry of the wormhole you have entered. For a wormhole without a horizon, the kind that theorists most seriously consider as a candidate for traversal, there is another critical feature that distinguishes it from a black hole in a deeply physical sense. In a black hole, as you approach and cross the event horizon, the light cones, the mathematical structures that define which directions in spacetime are available to you, which futures are accessible, begin to tip. At the horizon, they tip so far that all future-pointing directions aim inward. You cannot move outward. You cannot even stay still. The geometry forces you deeper, and there is no returning. In a horizon-free wormhole throat, this tipping does not occur. The light cones, though distorted by the intense curvature around them, remain open in both directions along the throat. You can, at least in principle, turn around. You are not trapped by the geometry. The future includes the possibility of going back the way you came. This is the difference between a passage and a trap. But whether the wormhole is genuinely two-way depends on more than just the presence or absence of a horizon. Some wormhole solutions are one-way, not because they possess a classical horizon, but because the geometry is time asymmetric in a way that funnels travelers through in only one direction. The throat, in these cases, acts less like a corridor and more like a valve. Matter can flow through in one direction but cannot return against the geometric current. The mathematics permits this without requiring a horizon in the traditional sense. The asymmetry is subtler, built into the curvature of the interior in a way that steers all time-forward paths toward the exit. For a traveler inside such a geometry, the experience might not feel obviously constrained. There might be no moment of sudden realization that you cannot go back. The geometry would simply make return increasingly difficult, increasingly indirect, until the exit is the only direction that remains available. And then there is time itself. Inside the throat, the paths that light takes are skewed. Not just bent, skewed. The relationship between the direction light travels and the direction time flows is altered by the geometry in a way that has no everyday analogy. Light from the mouth you entered might appear behind you, shifted and distorted. Light from the exit mouth might arrive at strange angles, from directions that don't correspond intuitively to where the exit actually is. Your perception of the two ends of the wormhole, as experienced from the interior, does not map cleanly onto the geometry of either end as experienced from outside. Time, inside the throat, is not running the same way it runs on either side. This is a consequence that sits at the heart of why wormholes captivate physicists and dreamers alike. The interior of a wormhole can compress the experience of travel in a way that has no equivalent in ordinary space. A journey that, measured in the external universe, spans galactic distances, tens of thousands of light years, hundreds of thousands, more, can be reduced, inside the throat, to seconds. Not because the traveler is moving faster than light in any local sense, but because the geometry of the interior is simply not the same as the geometry of the exterior. The interior path and the exterior distance are different quantities, measured in different geometries, and they need not bear any proportional relationship to each other. Seconds of interior time. Galactic distances crossed. The mathematics does not forbid this. In certain well-studied models, it actively predicts it. And yet, and this is the part that stays with you quietly after everything else has been considered, you do not necessarily know where you will arrive. The destination of a wormhole is not guaranteed. It is not labeled. The exit mouth, if the wormhole is dynamic, if it is embedded in a spacetime that is itself evolving, if it connects to a region of the universe that has changed since the wormhole formed, that exit could open onto something entirely unexpected. A different region of space. A different moment in time. A place that, from where you started, is not simply far away but fundamentally unknown. You entered a geometry. You followed its curves. You emerged somewhere. Whether that somewhere is where you intended, whether it is even where the wormhole was pointing when you began, is a question that the mathematics does not always answer cleanly. Wormhole solutions that are static and perfectly symmetric offer predictable exits. but wormholes embedded in realistic, dynamic spacetimes, the kind that a universe like ours might actually produce, carry with them an irreducible uncertainty about what waits at the end. There is something strangely meditative about that. To enter a wormhole is to commit entirely to a geometry you cannot fully read from the inside. To trust the throat, the curvature, the exotic matter holding the passage open. To move through warped space and skewed time, through tidal forces that may be gentle or may be immense, through an interior whose length bears no reliable relationship to the distance outside, and to arrive, somewhere, without certainty about what that somewhere is. The universe, at its deepest geometric level, does not guarantee destinations. It only offers passages. Of all the strange things that happen inside a wormhole, time may be the strangest. Not because time disappears, or stops, or reverses in any simple dramatic way, but because the relationship between time at one mouth and time at the other, the way clocks tick, the way events order themselves, the way cause and effect are supposed to flow, all of that begins to come apart in ways that are mathematically precise and philosophically disquieting. It starts with something that general relativity already tells us about time and curved spacetime. Time runs at different rates in different gravitational environments. This is not a hypothesis or an approximation, it is one of the most thoroughly tested predictions in all of physics. A clock sitting deep in a gravitational well ticks more slowly than a clock far from any gravitational source. The stronger the curvature, the greater the difference. Two clocks, starting synchronized, placed in different gravitational environments, and brought back together will show different times. They will have aged differently. They will have measured different amounts of elapsed time for what was, from the outside, the same interval. Inside a wormhole, both mouths sit in their own gravitational and spatial environments, and the throat connecting them imposes its own pattern of curvature on time along its length. The result is that the two ends of a wormhole need not share the same clock. Time at one mouth can run faster or slower than time at the other, depending on the masses nearby, the velocities of the mouths if they are moving, and the specific geometry of the interior. And here is where something genuinely remarkable emerges. If you could move one mouth of a wormhole, accelerate it, carry it through space at high velocity, bring it into a strong gravitational field for a period and then withdraw it, the time dilation experienced by that mouth would cause it to fall out of synchrony with the other. One end would age less. One end would, in a precise and calculable sense, be shifted into the past relative to the other. Now imagine entering through the mouth that is further in the future and exiting through the mouth that is further in the past. You would emerge at an earlier time than when you entered. Not metaphorically. Not approximately. Earlier, in the same sense that yesterday is earlier than today. This is the mechanism by which physicists have shown that wormholes, if they exist and can be manipulated, could in principle function as time machines. Not through any exotic additional physics, not through any property beyond what general relativity already predicts, but simply through the accumulation of time dilation between the two mouths, and the shortcut that the throat provides between them. The idea is not fringe speculation. It was worked out carefully and published in serious scientific literature by Kip Thorne and his colleagues in the late 1980s, and it has been discussed, debated, and extended ever since. The mathematics is sound. The question of whether it is physically realizable is another matter entirely, but the mathematics does not object. What the mathematics does produce, in this scenario, is something that physicists call a closed time-like curve. A time-like curve is simply the path through spacetime traced by an object moving slower than light, a world line, the continuous record of an object's position through both space and time. Normally, time-like curves are open. They begin somewhere, they move forward in time, and they never loop back on themselves. Cause precedes effect. The future is ahead, and the past is behind, and the two do not meet. A closed time-like curve is a world line that loops. An object following it moves through space and time and eventually returns to the same point in space-time it started from, the same location, the same moment. It is a loop in time. A cycle with no beginning and no end. And inside certain wormhole geometries, closed time-like curves can exist. They are not inserted artificially. They emerge from the mathematics of the interior, from the combination of the throat's geometry and the time offset between its two mouths. A path that goes forward in time through ordinary space, enters one mouth, passes through the throat, and exits the other mouth into the past. That path, continued through space back to where it started, forms a closed loop. The implications of this are enormous and deeply unresolved. If closed time-like curves exist, then causality, the principle that causes precede their effects, that the past is fixed and the future is open, faces a profound challenge. You could, in principle, send a message to yourself before you send it. You could influence the events that led to your own existence. You could, in the most extreme formulations, create situations where an event causes itself, or prevents itself, and the resulting logical contradiction has no clean resolution. Physicists have spent considerable energy thinking about whether nature would permit this. Stephen Hawking famously proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire, through mechanisms not yet fully understood, to prevent closed time-like curves from forming in any physically realistic scenario. Quantum effects, he argued, would build up near a wormhole as it approached the conditions required for time travel, producing a feedback of radiation that would destroy the wormhole before it could be used as a time machine. Whether he was right remains an open question. The conjecture has not been proven. And the mathematics of the wormhole interior continues to permit, in principle, what intuition and causality would prefer to forbid. There is another layer to the strangeness of time inside the throat. In ordinary space-time, there is a natural way to divide the universe into a sequence of moments, a foliation, physicists call it, a way of slicing space-time into a stack of spatial snapshots, each one representing the universe at a different instant. This foliation is not unique. Different observers in relative motion will slice space-time differently, but there is a family of reasonable, well-behaved ways to do it, and they all share the same basic structure of time flowing forward from past to future. Inside a wormhole, this breaks down. There is no unique, natural way to slice the interior into moments of time. The geometry of the throat does not come equipped with a preferred time direction, a natural foliation, a clean sense of which events are simultaneous and which are not. the interior is, in this sense, temporally ambiguous. Different mathematical descriptions of the same wormhole interior can assign completely different time structures to it, and none of them is more correct than any other. This is deeply unsettling if you think about it carefully. It means that the interior of a wormhole does not have a story that can be told sequentially. There's no narrative of what happens inside the throat in which events can be cleanly ordered, first this and then that. The throat resists storytelling in the conventional sense. Relatedly, the interior geometry of a wormhole generally lacks what physicists call time reversal symmetry. The geometry going in one direction through time does not look the same as the geometry running in the reverse direction. The throat, in most realistic models, is not symmetric under the operation of reversing time, which means that the experience of entering is not the time reverse of the experience of exiting. The geometry has a preferred sense of direction, even when it lacks a preferred foliation. This asymmetry is subtle, but it is physically meaningful. It is part of what makes certain wormholes one way, and part of what makes the interior feel, in a deep sense, like a place with its own temporal character rather than a neutral passage. There are special models in which the interior is time symmetric. Perfectly symmetric wormhole solutions, built with idealized configurations of matter and geometry, can produce a throat that looks the same in both temporal directions. But these models are exceptional. They require precise fine-tuning of the geometry and the matter distribution. They are the theoretical ideal, not the generic case. In a universe that is dynamic, evolving, and filled with the messiness of real physical processes, such perfect symmetry would be extraordinarily unlikely to arise naturally. And then there is a possibility so strange that it connects wormhole physics to cosmology itself. The interior geometry of a wormhole can, in certain solutions, behave in a way that mimics what physicists call a cosmological bounce. A bounce, in cosmological terms, is an event in which the universe reaches a minimum size, a moment of maximum compression, and then expands again, rather than collapsing to a singularity. It is the theoretical alternative to a Big Bang with no before, the possibility that the universe has a prior history that was compressed and then rebounded into what we now inhabit. Inside a wormhole throat, the geometry can pass through an analogous minimum, a point of maximum contraction, and then expand again into the exit region. The throat reaches its narrowest point and opens back up. The mathematics of this interior contraction and re-expansion is structurally similar to the mathematics of a cosmological bounce, and this parallel is not merely superficial. It points to deep connections between wormhole physics and the large-scale evolution of the universe, between the geometry of a small throat in space and the geometry of the cosmos as a whole. Which naturally raises a question that has occupied physicists since wormholes were first seriously considered. What is holding this open? Because everything described so far, the traversable throat, the gentle tidal forces, the absence of a horizon, the passage of light in both directions, the entire structure that allows a wormhole to function as anything other than an instantaneously collapsing geometric artifact, all of it requires something. Something has to thread the throat. Something has to exert an outward pressure against the gravitational tendency of the wormhole to pinch off and seal itself. Gravity, left to its own devices, collapses things. It draws matter together. It tightens and compresses and seals. Without something actively resisting this tendency, a wormhole throat would collapse faster than light could cross it, making it impassable not just in practice but in principle. That something is what physicists call exotic matter. The word exotic here is not casual. It does not simply mean unusual or unfamiliar. It means something with a specific and deeply strange physical property, negative energy density. Ordinary matter and energy have positive energy density. They curve spacetime inward, toward themselves. They attract. They focus light. They collapse. This is the behavior we are familiar with, the behavior that builds stars and planets and holds galaxies together. Exotic matter, with negative energy density, does the opposite. It curves spacetime outward. It defocuses light rather than focusing it. And most critically for a wormhole, it repels rather than attracts. Negative energy is not a purely theoretical invention without grounding in real physics. It appears, in small and carefully defined quantities, in certain quantum mechanical effects. The Casimir effect, the measurable attractive force between two uncharged metal plates held very close together in a vacuum, is understood to arise from a configuration of quantum vacuum energy that includes regions of negative energy density between the plates. This has been measured in laboratories. It is real. The effect is tiny, but the principle is established. What wormhole physics requires is negative energy on a scale that is, by any current measure, fantastically beyond what we can produce or observe. The amount of exotic matter needed to hold open a wormhole of any useful size, wide enough for a spacecraft, or even just wide enough for a beam of light, is, in most theoretical estimates, comparable to the mass energy of a planet, or a star, expressed as negative energy. Whether nature produces exotic matter in such quantities anywhere in the universe is completely unknown. But the mathematics is clear about what is needed. To hold the throat open, to keep the geometry from collapsing, to maintain the passage against the relentless inward pressure of gravity, you need something that pushes back. Something that repels. Something that carries energy of the wrong sign, the sign that ordinary matter never has, the sign that makes the equations work in the direction of openness rather than closure. The wormhole needs the universe to contain something genuinely strange at its foundation. Something that curves spacetime in reverse. Something that makes room where gravity would otherwise leave none. Whether that something exists, in the quantities required, in the places required, is a question the universe has not yet answered. And so the wormhole remains, for now, a feature of the mathematics. Patient. Open in the equations. Waiting for the physics to catch up. Nothing in the universe stays open forever without a reason. A flame needs fuel. A star needs the pressure of nuclear fusion pushing outward against the crush of its own gravity. Even the most stable structures in nature are, at their deepest level, a balance of competing forces, and the moment that balance tips, change follows quickly. A wormhole is no different. For all the mathematical elegance of a traversable throat, for all the careful construction of exotic matter and negative energy and precisely shaped metrics, there is a fragility built into the geometry that physicists have never been able to engineer away entirely. The wormhole, in most theoretical models, is not a stable structure. It is a balance. And balances, especially delicate ones, can be broken. The most fundamental form of this instability is gravitational. The throat of a wormhole is held open against the natural tendency of spacetime to collapse. The exotic matter threading it pushes outward, the curvature curves in a direction that keeps the passage clear. But this is a dynamic equilibrium, not a solid structure. If the balance is disturbed, if the exotic matter distribution shifts, if external matter falls in, if any perturbation tips the geometry even slightly out of its carefully maintained configuration, the throat responds. It begins to contract. And once contraction begins, it tends to accelerate. The geometry feeds on itself. The narrowing increases the curvature, the increased curvature accelerates the narrowing, and the throat pinches off. What is particularly striking about this process is that it happens without warning to anyone inside. There is no local signal when the throat begins to collapse. No alarm, no change in the immediate environment that a traveler moving through the interior could detect and respond to. The pinching off of a wormhole throat is a global property of the geometry. It involves the behavior of the spacetime as a whole, and global properties are invisible to local measurements. A traveler moving through the throat in the moments before it collapses would see ordinary, if exotic, spacetime. The light around them would be distorted in the usual ways. The tidal forces would feel as they always had. Nothing in their immediate surroundings would signal that the passage was closing. And then it would be closed. This is one of the more quietly unsettling aspects of wormhole physics. The very feature that makes the interior navigable, the fact that it feels locally like open space, without horizons or sharp boundaries, is the same feature that makes the collapse invisible from within. You cannot see the walls closing because there are no walls. The geometry simply stops being traversable, and there is no local announcement of when that happens. The instability becomes even more pronounced when quantum mechanics enters the picture. In a purely classical description, treating spacetime as a smooth, continuous geometric structure with no quantum effects, a wormhole can be held in a stable configuration as long as the exotic matter is correctly arranged. But spacetime is not purely classical. At the quantum level, the vacuum itself is not empty. It seethes with fluctuations, tiny, transient variations in the energy of empty space, particles flickering in and out of existence, fields oscillating at every frequency. These fluctuations are real, they carry energy, and they interact with the curvature of spacetime. Near a wormhole throat, these quantum vacuum fluctuations become a serious problem. The curved geometry of the throat focuses and amplifies certain modes of quantum fluctuation in a way that builds up energy near the throat rather than dispersing it. This buildup of quantum energy acts back on the geometry, altering the curvature in ways that tend to destabilize rather than stabilize the throat. Physicists have calculated that this quantum feedback is not a small correction to an otherwise stable system. In many models, it is sufficient on its own to destroy the throat before any macroscopic traveler could cross it. This was part of Hawking's argument for the chronology protection conjecture. The quantum feedback that destabilizes a wormhole being manipulated toward time travel geometry is not just a hypothetical concern. It is a calculable effect, derived from the same quantum field theory that underlies the rest of modern physics. The fluctuations grow. The throat destabilizes. The passage closes. And the quantum fluctuations responsible for this do not need to be large to be devastating. This is perhaps the most sobering aspect of wormhole instability. You might imagine that a throat could be made robust simply by making it massive, or by using large amounts of exotic matter, or by engineering the geometry with sufficient precision. But quantum fluctuations are irreducible. They cannot be shielded against or engineered away. They are a fundamental property of the quantum vacuum, present at every point in space, at every moment. And in the intensely curved geometry of a wormhole throat, even the smallest fluctuations, the irreducible minimum of quantum noise that the uncertainty principle demands be present, can be enough to nudge the geometry out of its equilibrium. Tiny perturbations. Enormous consequences. The throat responds to quantum whispers with catastrophic sensitivity. This sensitivity extends beyond quantum effects alone. Wormhole throats are also unstable under slow, gradual changes in external conditions, not just sudden perturbations but gentle, long-term drifts in the surrounding spacetime environment. If the mass distribution near one mouth changes slowly, if a nearby star drifts closer over millions of years, if the cosmological expansion of the universe alters the global geometry in which the wormhole is embedded, these slow external changes can accumulate and eventually push the throat out of stability. The wormhole is not simply vulnerable to being struck. It is vulnerable to being gently, patiently eroded by the universe around it. This picture of instability, quantum, classical, sudden, and slow, raises an obvious question about what kind of structure could even attempt to maintain a wormhole throat in the first place. One answer that theorists have explored involves a specific and elegant construction called a thin-shell wormhole. Rather than threading an entire volume of space with exotic matter, a thin-shell wormhole concentrates all of its structure, all of the unusual matter and energy required, into a single surface. A shell. A membrane of zero thickness, positioned at the throat, doing all of the geometric work of holding the passage open without possessing any interior volume of its own. This shell is often modeled as a domain wall, a surface where some field transitions sharply from one value to another, forming a boundary with its own surface tension, its own energy density, and in the case of a wormhole throat, a negative energy density that provides the outward pressure needed to prevent collapse. The entire wormhole, in this construction, is essentially built around this membrane. The throat is the shell. Everything else, the two exterior regions that the wormhole connects, is constructed around it. What makes the thin shell construction mathematically elegant is its simplicity. Instead of dealing with a complicated, volumetric distribution of exotic matter filling an extended region of space, the physicist works with the surface itself. The junction conditions, the mathematical rules that govern how two regions of spacetime can be joined across a surface, are well established, and a thin-shell wormhole is, in essence, a careful application of those junction conditions to connect two otherwise separate geometries at a single spherical surface. The throat in this model has no interior in the usual sense. It is a surface, not a volume. A sphere, not a tunnel. This requires a slight revision of the intuitive picture of a wormhole as a long passage. In the thin-shell construction, there is no tube, no extended corridor, no region of space that you spend time traveling through. There is only the shell, the junction surface, and on each side of it lies a separate region of spacetime. Crossing the wormhole means crossing the shell. Nothing more. The passage is instantaneous in the sense that the shell itself has no thickness. The two exterior regions joined by the shell are, in the simplest versions of the construction, taken from flat spacetime, regions of ordinary, uncurved space, joined across this spherical membrane as though two empty universes had been opened up and sutured together at a single spherical cut. The shell holds the geometry together. The flatness of the regions it connects means that outside the shell, spacetime behaves completely normally. All the strangeness, all the exotic physics, is concentrated entirely at the throat itself. This is a powerful simplification. It allows physicists to study the stability and behavior of wormhole throats without having to solve the full, complicated equations for exotic matter distributed through a volume. The thin-shell formalism has been used to explore a wide range of wormhole properties, from stability under perturbations to the effects of charge and rotation, and it remains one of the most productive tools in the theoretical study of wormhole geometry. But the thin-shell wormhole does not escape the fundamental challenge. The shell itself, to do its job, must have negative energy density. The domain wall must push outward rather than inward. The membrane that holds the geometry together must be made of something that ordinary matter is not. The construction is elegant, but it does not dissolve the need for exotic matter. It concentrates it, focuses it into a single surface, but it does not eliminate it. And this has led physicists to ask a deeper and more radical question. Is exotic matter actually necessary? For most of the history of wormhole research, the answer appeared to be yes, unavoidably, fundamentally yes. The mathematical theorems governing the behavior of geodesics, the paths that light and matter follow through curved spacetime, seem to demand it. A specific result called the topological censorship theorem, along with related energy condition results, appeared to show that any traversable wormhole, in standard general relativity, requires matter that violates the standard energy conditions, matter with negative energy density, exotic matter. But general relativity is not the only theory of gravity. It is the best tested theory of gravity we have, the one that has survived every experimental challenge thrown at it for over a century. But it is also almost certainly not the final word. The universe at the smallest scales requires quantum mechanics, and quantum mechanics and general relativity are not yet fully reconciled. At energies and curvatures far beyond what we can currently probe, the equations of general relativity are expected to be replaced by something more complete, a theory of quantum gravity that reduces to general relativity in the appropriate limit but contains new physics beyond it. In the meantime, physicists have explored what are called modified gravity theories, extensions or alternatives to standard general relativity that introduce additional terms, additional fields, or additional geometric structure into the equations governing spacetime. These theories are motivated not just by the desire to accommodate wormholes but by a range of cosmological puzzles, including the nature of dark energy and the behavior of gravity on the largest scales. And some of these modified gravity theories change the wormhole picture in a striking way. In certain modified gravity frameworks, the additional geometric structure built into the theory can itself provide the outward pressure that a wormhole throat requires, without any exotic matter at all. The modification to the gravitational equations produces, effectively, a geometric contribution that mimics the effect of negative energy, holding the throat open through the structure of the theory itself rather than through any unusual material threading the wormhole. This is a remarkable possibility. It would mean that the requirement for exotic matter is not a fundamental feature of wormhole physics but an artifact of working within the specific framework of standard general relativity. Step outside that framework, into a more general theory of gravity, and the obstacle dissolves. The wormhole becomes, at least in principle, a structure that the laws of physics as we understand them, extended slightly beyond their current form, might actually permit without requiring ingredients that seem physically unrealizable. Whether any of these modified gravity theories actually describe the real universe is a separate question, and one that remains open. The modifications they introduce have consequences beyond wormholes, and those consequences must be tested against observations. Some modified gravity theories are already constrained by what we observe. Others remain viable. But the possibility that wormholes might not need exotic matter, that the geometry itself, in the right theory of gravity, might do the work, is one of the most energizing ideas in the field. It moves wormholes from the category of structures that are mathematically consistent but physically implausible to the category of structures that might, just might, arise naturally in a universe described by the right fundamental theory. The throat, for so long held open only by the impossible, might yet find a more natural support. The search for a wormhole that does not require the impossible has quietly become one of the most creative areas of theoretical physics. For decades, the exotic matter requirement sat at the center of wormhole research like an uncomfortable admission. Yes, the geometry works, yes, the mathematics is consistent, but the ingredient list includes something that may not exist in any useful quantity anywhere in the universe. Modified gravity offered one way around this. But physicists, characteristically unwilling to commit to a single approach when the problem is interesting enough, have pursued several others simultaneously. And what has emerged is a surprisingly rich landscape of possibilities, each one holding the throat open by a different mechanism, each one pointing to a different corner of fundamental physics. Some of the most intriguing proposals do not require modifying gravity at all. They work within standard general relativity but look more carefully at what kinds of matter and energy already exist in the universe, and ask whether any of them might do the job. Dark matter is the most abundant form of matter in the cosmos. It outweighs ordinary matter by roughly 5-to-1. It fills the halos of galaxies, extending far beyond the visible stars and gas, providing the gravitational scaffolding within which galaxies form and persist. We cannot see it directly. We have not detected it in any laboratory. We know it exists because of its gravitational effects on everything around it, the rotation curves of galaxies, the bending of light across galaxy clusters, the large-scale structure of the universe. And we do not know, with certainty, what it is. This uncertainty is, for wormhole physics, an opportunity. Certain theoretical models of dark matter assign it properties that differ in important ways from ordinary matter. Some proposals involve dark matter with a non-trivial equation of state, a relationship between its pressure and energy density that, in certain regimes, could provide the outward pressure needed to hold a wormhole throat open. If a sufficiently concentrated dark matter halo forms around a wormhole mouth, or if a wormhole forms within a dark matter concentration, the combined effect of the dark matter's unusual pressure properties might substitute, at least partially, for exotic matter. This is speculative. The specific dark matter properties required are not guaranteed by any confirmed model. But it is speculative in the best sense, grounded in real physics, constrained by real observations, and pointing toward tests that future dark matter experiments might be able to address. If the right kind of dark matter exists, and if it can accumulate in the right configurations, the universe might already contain the ingredient for traversable wormholes hidden inside the invisible halos that surround every galaxy. The idea that ordinary fermions might hold a wormhole open is, if anything, even more surprising. Fermions are the particles of matter, electrons, protons, neutrons, quarks. They are the building blocks of everything you can touch. And they have a property, rooted in quantum mechanics, called the Pauli exclusion principle. No two fermions can occupy the same quantum state in the same place at the same time. This principle is what gives matter its solidity. It is why you cannot push your hand through a table. It is why neutron stars, composed of densely packed neutrons, resist gravitational collapse. The exclusion principle generates a pressure that pushes back. In certain highly compressed configurations, this fermionic pressure can be enormous. And in some theoretical analyses, configurations of ordinary fermionic matter threading a wormhole throat have been shown to generate sufficient pressure, through purely quantum mechanical means, to support the throat against collapse, without invoking any matter with negative energy density, without requiring anything that does not already exist in the standard model of particle physics. The implications of this are profound. It would mean that the most familiar stuff of which the universe is made, the matter in stars, in planets, in your own body, contains, at the quantum level, a pressure that is at least theoretically capable of holding open the geometry of spacetime. The barrier between the exotic and the ordinary becomes, in this picture, somewhat less absolute. Quantum fields more broadly offer another avenue. Even in a complete vacuum, a region of space containing no particles, no classical matter, quantum fields are present. They are always present. The vacuum is not empty in quantum field theory. It is a state of minimum energy, but that minimum is not zero, and the fields that pervade the vacuum have fluctuations, correlations, and stress energy that contribute to the geometry of spacetime. When quantum fields are threaded through a wormhole throat, forced, by the topology of the geometry, to exist in a space with non-trivial connectivity, their vacuum state changes. The boundary conditions imposed by the wormhole geometry alter the modes of the fields, and the resulting changes in the vacuum energy can, in certain configurations, produce a stress energy tensor with the right properties to support the throat. This is related to the Casimir effect, but applied to the global topology of the spacetime rather than to the gap between metal plates. The wormhole itself, by virtue of its topology, modifies the quantum vacuum within it in a way that might contribute to its own stability. The geometry affects the fields, and the fields affect the geometry, in a self-consistent loop that could, in principle, sustain the passage. Then there are topological defects. In the early universe, as the cosmos cooled from its initial extreme temperatures, various phase transitions occurred, moments when the universe's fundamental fields settled into their current configurations, analogous to the way water freezes into ice. In such transitions, defects can form, places where the field cannot settle cleanly, where different regions of the settling field meet in a way that leaves a permanent knot or boundary in the structure of space. These are topological defects, and they come in several varieties: cosmic strings, domain walls, magnetic monopoles, and global monopoles. A global monopole is a particular kind of defect, a point-like knot in a field that carries a kind of topological charge, surrounded by a pattern of field lines extending outward in all directions. Global monopoles have a distinctive effect on the spacetime geometry around them. Certain theoretical models of dark matter assign it properties that differ in important ways from ordinary matter. Some proposals involve dark matter with a non-trivial equation of state, a relationship between its pressure and energy density that, in certain regimes, could provide the outward pressure needed to hold a wormhole throat open. If a sufficiently concentrated dark matter halo forms around a wormhole mouth, or if a wormhole forms within a dark matter concentration, the combined effect of the dark matter's unusual pressure properties might substitute, at least partially, for exotic matter. This is speculative. The specific dark matter properties required are not guaranteed by any confirmed model. But it is speculative in the best sense, grounded in real physics, constrained by real observations, and pointing toward tests that future dark matter experiments might be able to address. If the right kind of dark matter exists, and if it can accumulate in the right configurations, the universe might already contain the ingredient for traversable wormholes hidden inside the invisible halos that surround every galaxy. The idea that ordinary fermions might hold a wormhole open is, if anything, even more surprising. Fermions are the particles of matter, electrons, protons, neutrons, quarks. They are the building blocks of everything you can touch. And they have a property, rooted in quantum mechanics, called the Pauli exclusion principle. No two fermions can occupy the same quantum state in the same place at the same time. This principle is what gives matter its solidity. It is why you cannot push your hand through a table. It is why neutron stars, composed of densely packed neutrons, resist gravitational collapse. The exclusion principle generates a pressure that pushes back. In certain highly compressed configurations, this fermionic pressure can be enormous. And in some theoretical analyses, configurations of ordinary fermionic matter threading a wormhole throat have been shown to generate sufficient pressure, through purely quantum mechanical means, to support the throat against collapse, without invoking any matter with negative energy density, without requiring anything that does not already exist in the standard model of particle physics. The implications of this are profound. It would mean that the most familiar stuff of which the universe is made, the matter in stars, in planets, in your own body, contains, at the quantum level, a pressure that is at least theoretically capable of holding open the geometry of spacetime. The barrier between the exotic and the ordinary becomes, in this picture, somewhat less absolute. Quantum fields more broadly offer another avenue. Even in a complete vacuum, a region of space containing no particles, no classical matter, quantum fields are present. They are always present. The vacuum is not empty in quantum field theory. It is a state of minimum energy, but that minimum is not zero, and the fields that pervade the vacuum have fluctuations, correlations, and stress energy that contribute to the geometry of spacetime. When quantum fields are threaded through a wormhole throat, forced, by the topology of the geometry, to exist in a space with non-trivial connectivity, their vacuum state changes. The boundary conditions imposed by the wormhole geometry alter the modes of the fields, and the resulting changes in the vacuum energy can, in certain configurations, produce a stress energy tensor with the right properties to support the throat. This is related to the Casimir effect, but applied to the global topology of the spacetime rather than to the gap between metal plates. The wormhole itself, by virtue of its topology, modifies the quantum vacuum within it in a way that might contribute to its own stability. The geometry affects the fields, and the fields affect the geometry, in a self-consistent loop that could, in principle, sustain the passage. Then there are topological defects. In the early universe, as the cosmos cooled from its initial extreme temperatures, various phase transitions occurred, moments when the universe's fundamental fields settled into their current configurations, analogous to the way water freezes into ice. In such transitions, defects can form, places where the field cannot settle cleanly, where different regions of the settling field meet in a way that leaves a permanent knot or boundary in the structure of space. These are topological defects, and they come in several varieties: cosmic strings, domain walls, magnetic monopoles, and global monopoles. A global monopole is a particular kind of defect, a point-like knot in a field that carries a kind of topological charge, surrounded by a pattern of field lines extending outward in all directions. Global monopoles have a distinctive effect on the spacetime geometry around them. They produce a solid angle deficit, a kind of geometric shortage in the space surrounding them, as though a wedge had been removed from the three-dimensional space around the defect and the edges joined together. This altered geometry can, in certain configurations, support wormhole-like structures. The topological charge of the monopole threads the throat, the geometric deficit shapes the surrounding space, and the result is a wormhole geometry that is sourced not by exotic matter in the traditional sense but by the topological properties of a field defect. Global monopoles are not confirmed to exist, but they are predicted by a range of theoretical models of the early universe, and their gravitational signatures would be distinctive enough to search for observationally. There is one more factor that influences wormhole stability in ways that are subtle but physically significant. Lorentz invariance is the symmetry at the heart of special relativity, the principle that the laws of physics are the same for all observers moving at constant velocities, that there is no preferred frame of reference, that space and time transform into each other in a specific, symmetric way. It is one of the most precisely tested symmetries in physics. And yet, in some theoretical frameworks, particularly those attempting to reconcile gravity with quantum mechanics, Lorentz invariance may be slightly broken at extremely high energies or small scales. There may be a preferred frame at the deepest level of physics, a frame associated with whatever fundamental structure underlies spacetime itself. If Lorentz invariance is violated, even slightly, the equations governing wormhole geometry change. The parameters describing that violation feed into the stability conditions for the throat. In some models, Lorentz violating terms act to stabilize configurations that would otherwise be unstable, effectively providing an additional geometric resistance to collapse. In others, they make stability harder to achieve. The effect depends on the specific form of the violation and the specific wormhole geometry, and the parameter space is large. But the general point is significant. The stability of a wormhole is sensitive to the deep symmetry structure of the physical laws that govern it. If those laws contain symmetry breaking at their foundation, the wormhole feels it. All of this, the dark matter halos, the fermionic pressure, the quantum vacuum fields, the topological defects, the Lorentz violating parameters, represents classical and semi-classical physics pushing toward the boundary of something deeper. Something that the theories we have can point toward but not fully describe. That boundary is the quantum realm of gravity itself. And at that boundary, the nature of wormholes changes entirely. To understand why, you need to think about what space looks like at the very smallest scales. At the scales of everyday life, space appears smooth and continuous, a seamless medium through which objects move and in which events occur. At the atomic scale, matter is granular, but space itself still appears to be a smooth backdrop. At smaller and smaller scales, quantum mechanics makes itself felt in more and more significant ways. But at one particular scale, the Planck scale, approximately 10 to the power of -35 meters, physicists believe that the smooth picture of spacetime breaks down entirely. At the Planck scale, quantum fluctuations in the geometry of spacetime itself become so large and so rapid that the familiar picture of a smooth, continuous space ceases to apply. Spacetime becomes something else, something turbulent and granular and uncertain, fluctuating wildly from moment to moment and point to point. This theoretical picture was given a vivid name by John Wheeler, one of the great architects of general relativity, quantum foam. The idea is that at the Planck scale, spacetime is not a quiet, smooth medium. It is a seething, fluctuating foam, a constantly changing topology, a geometry that is being created and destroyed and rearranged on timescales so short and at distances so small that no current instrument could ever hope to resolve them. In this foam, the topology of space is not fixed. It changes. It bubbles. And among the topological structures that appear and disappear in this quantum turbulence are microscopic wormholes. Not traversable passages between distant regions of the universe. Not corridors that a spacecraft could enter. Something far smaller and far stranger, wormhole-like structures at the Planck scale, flickering in and out of existence as part of the natural quantum dynamics of spacetime itself. Topological handles in the foam, momentary connections between nearby points in space, existing for times so brief that they are effectively instantaneous by any measure accessible to physics above the Planck scale. These microscopic wormholes are a prediction, or more precisely, a theoretical expectation, of a fully quantum theory of gravity, a theory that does not yet fully exist but whose qualitative features physicists have been able to sketch. They are wormholes not as exceptional structures held open by unusual matter but as ubiquitous features of the quantum geometry of space, present everywhere, always, invisible to us only because of the enormous gap between the Planck scale and the scales at which we make observations. This is a striking inversion of the usual picture. Instead of asking how a wormhole could form and be maintained in an otherwise smooth spacetime, quantum foam suggests that spacetime at its deepest level is already full of wormholes, that the smooth space we inhabit is an average, an approximation, a large-scale description of something that is, at its foundation, topologically intricate in ways we cannot directly perceive. And if microscopic wormholes exist in the quantum foam today, there is reason to think they also existed, in potentially very different forms, at the very beginning of the universe. In the earliest moments after the Big Bang, the universe was not merely hot and dense. It was in a state where quantum gravitational effects were dominant, where the curvature of spacetime was so extreme, and the energy so enormous, that the classical description of general relativity was insufficient. The universe, at its birth, was a quantum gravitational system, and the structures that emerged from that early period were shaped by quantum gravitational processes. Among those structures, theorists have proposed, may have been primordial wormholes, wormhole-like geometries that formed during the Planck epoch, the universe's earliest and most extreme phase, and that may have left some signature on the spacetime we inhabit today. These primordial wormholes would not have formed through the collapse of matter or the manipulation of exotic fields. They would have arisen directly from the quantum fluctuations of the early universe's geometry, as natural features of a spacetime in its most wildly quantum state. Whether such primordial wormholes survived into the present universe, whether they grew or shrank as the universe expanded, whether they left any observable trace in the cosmic microwave background or the large-scale structure of space, these are open questions, largely beyond the reach of current theory and certainly beyond the reach of current observation. But they point towards something that gives the entire subject of wormholes a different quality when you step back and look at it whole. We began with a simple geometric concept, two mouths linked by a throat, an extreme curvature of spacetime. We moved through the optics of approach, the physics of the interior, the strangeness of time, the fragility of stability, the search for mechanisms that might hold the throat open. And now we arrive at the possibility that wormholes are not rare, exotic, artificially constructed objects in an otherwise smooth universe. They may be fundamental. They may be everywhere, invisibly small, perpetually present, woven into the quantum fabric of space itself. The universe may be less of an empty expanse and more of a deeply, quietly connected thing, stitched together at scales too small to see, by passages too brief to measure, in ways that our largest theories are only beginning to describe. When the universe was young and small enough that quantum gravity ruled everything, the wormholes that flickered through the primordial foam were not the stable, carefully balanced structures that theorists would later spend decades trying to construct. They were wild things. Creatures of the quantum turbulence that defined those first impossible moments. And then the universe expanded. As space stretched outward in the aftermath of the Big Bang, anything embedded in that geometry stretched with it. Primordial wormholes, if they existed, would not have remained at the Planck scale indefinitely. The expansion of the universe would have pulled at them, drawn their mouths apart, elongated their throats, scaled them up from the quantum foam into something larger. Whether they survived this stretching, whether the geometry held together under the stress of cosmic expansion or simply tore apart, is a question that depends on the specifics of quantum gravitational dynamics that we cannot yet calculate with confidence. But the possibility is there. The universe's expansion is not just a backdrop to the story of wormholes. It is an active force that may have shaped them, enlarged them, distributed them across the cosmos in patterns that reflect the geometry of the early universe itself. As wormholes transition from the classical to the quantum picture, the behavior of matter near the throat changes in ways that are both strange and deeply revealing. At the quantum level, particles do not simply travel through a wormhole the way a spacecraft might. They behave as quantum objects, with wave functions that spread, superpose, and interfere. A quantum particle approaching a wormhole throat does not choose a single path and follow it. Its wave function explores multiple possibilities simultaneously, including the possibility of passing through the throat and the possibility of reflecting back, and the probabilities of each outcome are governed by the detailed quantum mechanics of the geometry. This leads to effects that have no classical analog. A particle's wave function can partially thread the throat and partially remain outside, creating a quantum superposition of being on both sides simultaneously. The coherence of this superposition, how long it persists before decoherence destroys it, depends sensitively on the nature of the wormhole geometry and the environment surrounding it. And near the throat, something else happens that echoes one of the most important discoveries in the history of black hole physics. Stephen Hawking showed in 1974 that black holes are not perfectly black. The quantum behavior of fields near the event horizon causes black holes to emit a faint thermal radiation, particles created in pairs near the horizon, one falling inward and one escaping outward, slowly carrying away the black hole's mass over time. This Hawking radiation is a purely quantum effect, invisible in any classical description of a black hole, and its discovery transformed our understanding of the relationship between gravity, quantum mechanics, and thermodynamics. Wormholes exhibit an analogous effect. The curved geometry near the throat, and particularly any horizon-like structure associated with it, produces a similar creation of particle pairs, one threading the throat in one direction, one escaping or threading in the other. This Hawking-like radiation near the wormhole throat is not identical to black hole Hawking radiation, because the geometry is different, but it arises from the same fundamental mechanism, the quantum vacuum responding to the curvature of spacetime by producing particles where a classical description would see only empty space. The implications of this are significant. Just as Hawking radiation slowly evaporates a black hole, Hawking-like radiation from a wormhole throat could, over time, affect the stability of the geometry. The energy carried away by this radiation must come from somewhere, and in the context of a wormhole, that somewhere is the structure of the throat itself. Whether this effect accelerates collapse or can be compensated by the exotic matter supporting the throat is model-dependent, but it cannot be ignored in any complete quantum treatment of wormhole physics. There is, however, a form of travel through a wormhole that these quantum effects do not obviously prohibit. Information. Not matter, not energy in the form of particles, but information in the abstract sense, the pattern, the quantum state. Certain theoretical analyses suggest that while the physical traversal of a wormhole by matter may be prevented or made implausible by instability, quantum effects, or the absence of exotic matter, the transmission of information through the wormhole geometry may be a different matter. The quantum state of a system, the full description of its configuration at the quantum level, might be transferable through the throat in ways that do not require the physical passage of any material object. This idea sits at the intersection of quantum information theory and quantum gravity, and it connects naturally to what is perhaps the deepest and most surprising idea in modern theoretical physics: the relationship between wormholes and quantum entanglement. Quantum entanglement is one of the most thoroughly verified and least intuitively graspable features of quantum mechanics. When two particles interact in the right way, they can become entangled. Their quantum states become correlated in a way that persists regardless of the distance between them. Measuring one particle instantaneously determines certain properties of the other, no matter how far apart they are. This correlation is not due to any hidden classical information shared between the particles. It is a genuine quantum connection, non-local in a way that no classical physics can replicate, and it has been tested in laboratories around the world with extraordinary precision. For most of the history of physics, entanglement and wormholes were considered completely separate subjects. Entanglement was a feature of quantum mechanics. Wormholes were a feature of general relativity. The two theories occupied different domains, and their connection was not obvious. Then, in 2013, theoretical physicists Juan Meldacena and Leonard Susskind proposed something that changed the conversation entirely. They suggested that entanglement and wormholes are not merely analogous. They are the same thing. Their proposal, expressed in the deceptively simple equation ER equals EPR, equates the Einstein-Rosen bridge, the wormhole, with the Einstein-Podolsky-Rosen pair, the entangled particles. The ER in the equation refers to the 1935 paper by Einstein and Rosen describing wormholes. The EPR refers to the 1935 paper by Einstein, Podolsky, and Rosen describing quantum entanglement. Both papers were written in the same year, by some of the same authors, describing what appeared to be completely separate phenomena. Meldacena and Susskind argued that they are not separate. That whenever two systems are quantum entangled, there is a sense in which they are connected by a wormhole-like geometric structure in the underlying spacetime. Not necessarily a wormhole that anything could travel through, but a geometric connection, a non-local link in the fabric of spacetime, that is the gravitational dual of the quantum entanglement between the systems. This is a profound and still debated idea. but it has gained significant traction because it fits naturally into a broader framework called the holographic principle, and specifically into a powerful theoretical construction called the ADS/CFT correspondence, a duality between a theory of gravity in a certain kind of spacetime and a quantum field theory living on the boundary of that spacetime. In this framework, the interior of a wormhole, the throat, the bridge between two regions, has a holographic structure. Its geometry is not fundamental. It emerges from the quantum information encoded in the entanglement between the boundary systems. The interior of the wormhole is, in a precise mathematical sense, a projection of the entanglement structure of the quantum systems at its boundaries. This means that entanglement is not just a quantum correlation between particles. It is, in this picture, the substance from which geometry is built. The wormhole's interior does not exist independently of the quantum state of the systems at its ends. It is encoded in that quantum state. It emerges from it. Entanglement is stored in geometry. Geometry is built from entanglement. These are not loose metaphors. In the ADS/CFT framework, they are precise, calculable relationships. The entanglement entropy between two regions of the boundary theory is proportional to the area of a surface in the bulk geometry. The geometry of the interior is reconstructed from the pattern of entanglement in the quantum state. If you could read the entanglement structure of the quantum systems at the two mouths of a wormhole, you would be reading the geometry of the interior itself. This connection between quantum bits of entanglement and geometric structure leads naturally to one of the most remarkable developments in recent physics: the simulation of wormholes on quantum computers. In 2022, a team of researchers at Google, working in collaboration with theoretical physicists including those who developed the ER=EPR framework, announced that they had used Google's Sycamore quantum processor to simulate a simple wormhole and observe the transmission of information through it. The experiment did not create a physical wormhole in space. It created a quantum system, a small number of qubits, that was mathematically equivalent to a holographic wormhole in a simplified model of quantum gravity, and it demonstrated that quantum information could be teleported from one set of qubits to another in a way that was consistent with traversal through the simulated wormhole geometry. The information entered one side of the simulated wormhole. It was scrambled by the quantum dynamics of the system, and it emerged, recognizably, from the other side, in a way that could only be explained, within the holographic framework, by its having traversed the simulated throat. This is not the same as transmitting information through a physical wormhole in space. The quantum computer is not a portal. The qubits are not mouths in the fabric of the cosmos. But the experiment is significant for a different reason. It demonstrates that the relationship between wormhole geometry and quantum entanglement is not merely a theoretical conjecture. It is something that can be implemented, tested, and observed in a real physical system, a quantum computer operating in a laboratory. The wormhole, in this context, becomes an information channel, a way of thinking about how quantum information moves through a maximally entangled quantum system. And the quantum computer becomes a tool for probing quantum gravity, not through telescopes or particle accelerators, but through the controlled manipulation of quantum bits. The connection between wormholes and quantum computing runs deeper still. The process of information traversal through the simulated wormhole involves quantum teleportation, a well-established quantum information protocol in which the quantum state of a system is transmitted from one location to another using entanglement and classical communication. In the holographic picture, this teleportation is dual to physical traversal through the wormhole geometry. The two descriptions, one in terms of quantum information operations, one in terms of a particle moving through a geometric throat, are different languages for the same physical process. A tiny quantum wormhole, in this framework, is an information channel in the most literal possible sense. It is a non-local connection between quantum systems, a way for information to move through a geometry that exists not in physical space but in the abstract space of quantum states, and it operates through the same principles of entanglement and quantum coherence that underlie all quantum information processing. What all of this points toward is something that would have seemed entirely inconceivable at the beginning of wormhole research: the idea that a wormhole is not primarily a feature of space, but a feature of information. That the geometry of the throat, the curvature that connects two distant regions, the bridge that allows passage from one place to another, all of this is, at its foundation, a pattern in the quantum information of the universe. A structure that emerges from entanglement the way that temperature emerges from the motion of atoms. A large-scale, geometric expression of something that is, at the deepest level, about the correlations between quantum degrees of freedom. Space, in this picture, is not the container that holds quantum systems. It is something that those systems build, collectively, through their entanglement, through the web of quantum correlations that connects every part of the universe to every other. Wormholes are the places where that building process produces something unexpected. Where the entanglement is so strong, so tightly non-local, that the geometry it generates contains a bridge, a passage, a connection that the smooth, classical picture of space would never have predicted. The universe, at its deepest level, may be less like a place and more like a calculation. And the wormhole may be what happens when that calculation connects two distant parts of itself in the most direct way it knows. The simulated wormhole on a quantum computer was not built the way you might build a bridge or a tunnel. There was no digging, no exotic matter, no careful engineering of spacetime curvature. It was built from quantum circuits, sequences of quantum operations applied to qubits, carefully designed to reproduce the mathematical relationships that define a holographic wormhole. This is a genuinely new way of thinking about what it means to create a wormhole. In the classical picture, a wormhole is a feature of geometry. You would build one, in principle, by assembling the right distribution of matter and energy in the right configuration to produce the desired curvature of spacetime. In the quantum information picture, a wormhole is a feature of entanglement structure. You build one by engineering the right quantum correlations between the right quantum systems. The geometry emerges from the entanglement, and so the wormhole emerges from the circuit. The specific circuits used are called teleportation circuits, quantum information protocols built around the principles of quantum teleportation, in which quantum states are transmitted between systems using entanglement and classical communication. In the holographic framework, quantum teleportation through a maximally entangled system is the quantum information dual of physical traversal through a wormhole. Engineer the teleportation correctly, And you have, in the mathematical sense that the holographic duality makes precise, engineered the wormhole. This framing carries a remarkable implication. It suggests that wormholes are not extraordinary geometric accidents or rare cosmological objects. They are, in the right theoretical language, a kind of computation. A way that a quantum system processes and transmits information. And any sufficiently entangled quantum system, any system with the right pattern of quantum correlations, can be described as containing a wormhole geometry in its dual gravitational description. But this engineered wormhole has properties that are not immediately obvious from the classical picture, and some of them are deeply strange. One of the most striking is what might be called a privacy horizon arising from the entanglement structure itself. In a classical wormhole, the question of whether information inside the throat is accessible to an outside observer is determined by the geometry, by whether there is a horizon, by whether light can escape from the interior. In the quantum picture, there is an analogous protection that arises not from geometry but from entanglement. The information that enters the wormhole, the quantum state that traverses the throat, is protected from outside observers by the structure of the entanglement itself. An observer who is not entangled with the right system, who does not have access to the correct quantum correlations, cannot reconstruct what passed through the wormhole. The entanglement acts as a kind of privacy shield, a horizon of information rather than a horizon of geometry. This privacy is not passive. It is actively maintained by a process called quantum scrambling. Quantum scrambling is what happens when a quantum system takes an input and spreads its information across all of its degrees of freedom in a way that makes the original information locally inaccessible. A scrambled quantum system looks, to any local observer, like a featureless thermal state, maximum entropy, maximum disorder, no trace of the original information visible in any small subsystem. But the information is not destroyed. It is hidden, distributed across the entire system in correlations that span all of its parts simultaneously. To recover the original information, you need access not to any single part of the scrambled system but to essentially all of it. Inside a wormhole, quantum scrambling is what protects the interior from outside observers. The information entering the throat is scrambled by the quantum dynamics of the system before it can be read by anyone without full access to the entangled quantum state. The interior is not hidden behind a geometric wall. It is hidden behind the complexity of the entanglement. The quantum chaos of the scrambling process is the lock, and the entanglement structure is the key. The connection between quantum chaos and the wormhole interior runs deeper than just this protective function. It turns out that the length of the wormhole interior, the distance from one mouth to the other as measured through the throat, is directly related to a quantity in quantum information theory called computational complexity. Computational complexity, in this context, measures how difficult it is to prepare a given quantum state starting from a simple reference state, essentially, how many quantum operations are required to build the state from scratch. In the holographic framework, the complexity of the quantum state at the boundary of the spacetime grows over time as the quantum system evolves. And as it grows, the interior of the corresponding wormhole grows longer. The throat extends. The bridge between the two sides becomes more elaborate, more convoluted, as the quantum dynamics of the boundary system becomes more complex. This gives the wormhole interior a quality that is genuinely unlike anything in classical geometry. The interior is not a fixed space. It grows. It evolves. Its length at any moment is a record of how much computational complexity has accumulated in the quantum state that generates it. Time, in the interior of the wormhole, is a measure of quantum complexity. And this growth is tied specifically to quantum chaos, the sensitivity of the quantum system's evolution to initial conditions, the speed at which information is scrambled, the rate at which correlations spread across the system. More chaotic quantum dynamics produce faster-growing wormhole interiors. The most chaotic quantum systems, those that scramble information at the maximum rate permitted by physics, produce wormhole interiors that grow at the maximum possible rate. The interior of the wormhole, in this picture, is not a serene geometric corridor. It is a dynamical, evolving space whose shape and size encode the quantum computational history of the systems at its boundaries. It grows longer and more complex as the quantum state evolves, tracing out the accumulating complexity of the entanglement structure. Some theoretical models give this growing interior a specific geometric character that is striking in its visual quality. The wormhole interior, in these models, does not have a simple cylindrical or spherical cross-section. It develops a more elaborate shape, elongated, segmented, with a geometry that physicists have described as caterpillar-shaped. The throat does not simply connect two spherical mouths through a smooth passage. It develops internal structure, regions of varying curvature, sections that expand and contract, as the quantum complexity encoded in its geometry accumulates over time. This caterpillar-like interior is not a fixed property of the wormhole. It is a snapshot of its quantum computational history. A longer, more elaborate interior means more complexity, more scrambling, more quantum chaos in the boundary system. The geometry of the wormhole is, in a precise sense, a picture of the quantum state that generates it. All of these developments, the entanglement, the scrambling, the complexity growth, the evolving interior, bear directly on one of the most contested and important problems in theoretical physics over the past 15 years. The firewall paradox. The firewall paradox arises from a conflict between three principles that physicists had previously assumed could all be simultaneously true. The first is the principle of unitarity, the quantum mechanical requirement that information is never truly destroyed, that the evolution of a quantum system is always reversible in principle. The second is the equivalence principle, the principle at the heart of general relativity that the experience of gravity is locally equivalent to the experience of acceleration, and that an observer falling freely through an event horizon should feel nothing unusual at the moment of crossing. The third is the requirement that the entropy of Hawking radiation is consistent with the black hole having a finite, well-defined quantum state. In 2012, a group of physicists, Almhiri, Merolf, Polchinski, and Sully, whose initials give the paradox its alternative name, AMPS, showed that these three principles cannot all be simultaneously satisfied. If unitarity holds and the Hawking radiation is in the right quantum state to preserve information, then the quantum field theory at the horizon requires that the correlations between the early and late Hawking radiation are inconsistent with the smooth, empty horizon that the equivalence principle demands. Instead, the horizon would be a region of dramatically high energy, a firewall, that would incinerate any infalling observer rather than letting them pass through smoothly. The paradox forced a choice: unitarity, the equivalence principle, or some modification of our understanding of quantum field theory near horizons. None of the options was comfortable. The ER=EPR framework and the wormhole entanglement connection offer a potential resolution, though it remains a subject of active debate. In this resolution, the entanglement between early and late Hawking radiation is not a relationship between two separate quantum systems connected only abstractly. It is the same relationship as a wormhole. The early radiation and the late radiation are connected by a geometric bridge in the interior, a wormhole-like structure that threads through the interior of the black hole. This geometric connection is what encodes the correlations required by unitarity. In the smooth horizon, the absence of a firewall is preserved because the entanglement is expressed not as a high-energy quantum field state at the horizon but as a geometric feature of the interior. The infalling observer does not hit a wall of fire. Instead, the observer enters a region of spacetime that is geometrically connected, through the interior wormhole structure, to the distant Hawking radiation. The firewall is avoided because the geometry does the work that quantum field theory would otherwise do violently. Whether this resolution is correct is not yet established. The details are intricate and contested. But the direction it points is clear: the interior of a black hole and the interior of a wormhole are not separate from the quantum information of the systems at their boundaries. They are made of that quantum information. The geometry is the entanglement, expressed in the language of space. And with this understanding in place, the stage is set to extend the picture outward, into dimensions beyond the three of space and one of time that make up the space-time of everyday experience. The holographic framework in which all of this lives is itself a statement about extra dimensions. The ADS/CFT correspondence is a duality between a gravitational theory and a five-dimensional anti-de Sitter spacetime and a quantum field theory living on the four-dimensional boundary of that spacetime. The wormhole interior, in this framework, does not just live in the three dimensions of space that the quantum systems at its mouths inhabit. It lives in the five-dimensional bulk, the higher-dimensional spacetime of the gravitational theory. This is what brane models and string theory suggest more broadly. In these frameworks, the universe we inhabit is a four-dimensional surface, a brane, embedded in a higher-dimensional spacetime called the bulk. The extra dimensions are not the large, open dimensions of ordinary space. They are hidden, compactified, curled up at scales so small that they have no observable effect on any current experiment, accessible only to gravity and to the exotic structures that gravity permits. Wormholes, in brane models, are not confined to the brain. They can extend through the bulk, threading through the extra dimensions, connecting points on the brane that are far apart in the brane's four-dimensional geometry but potentially much closer when the extra-dimensional bulk is taken into account. The wormhole throat, in this picture, is a higher-dimensional object. It lives not in the three dimensions of space that we perceive but in the full five-dimensional spacetime of the bulk. The hidden extra dimensions are not merely a backdrop to this picture. They are part of the wormhole's structure. The geometry of the extra dimensions shapes the throat, determines its width, its stability, its behavior under perturbations. A wormhole that appears, from the brain's perspective, to connect two distant points in ordinary space may, in the bulk, be a relatively short and smooth structure, because the extra dimensions provide a more direct geometric route between those points. This is the higher dimensional analog of the wormhole's basic premise. Just as a wormhole in ordinary three-dimensional space provides a shortcut between distant points by threading through a fourth spatial dimension, a wormhole in brain-world cosmology provides a shortcut between distant points on the brain by threading through the fifth dimension of the bulk. In the interior of this wormhole, the throat that connects the two brain-world mouths lives entirely in the bulk. It is a region of five-dimensional spacetime, invisible to any observer confined to the brain, accessible only through the geometric connections that the bulk geometry permits. The idea that the interior of a wormhole exists in a higher dimensional space adds a quality to the concept that is difficult to fully articulate but easy to feel. The passage is not through the space we inhabit. It is through a space behind our space. A dimension that our instruments cannot directly probe, that our bodies cannot enter through any ordinary means, that exists, if these models are correct, as a vast, hidden arena within which the geometry of our universe is embedded like a surface in a volume. The wormhole is a door not just through space, but through dimensionality itself. A passage that leaves the familiar geometry of the brain, traverses the hidden bulk, and returns to the brain at a different point. The universe, in this picture, is larger than it looks. Larger in the most literal geometric sense, containing dimensions we cannot see, volumes we cannot measure, a space-time richer and more complex than the one our senses reveal. And wormholes are the structures that connect the visible surface of that space-time to its hidden depth. What lies in the bulk is not nothing. It is geometry. It is the space-time within which our universe is a single, luminous, four-dimensional slice, and through which, if the mathematics is right, the most extraordinary connections in the cosmos quietly thread. There is a certain point in any deep investigation of physics where the structures being studied stop feeling like objects in the universe and start feeling like windows into the universe's own logic. Wormholes crossed that threshold some time ago. What began as a geometric curiosity, an unusual solution to Einstein's equations, has become one of the most productive laboratories in theoretical physics, a place where the deepest questions about the nature of space, time, information, and gravity are being tested and refined. But before arriving at those questions, there are several more layers of the wormhole's geometry to explore. Layers that push the concept further than most introductions to the subject ever reach. The mathematical frameworks used to describe wormholes have, in recent years, been extended beyond the relatively familiar territory of Riemannian geometry, the geometry of smooth, curved spaces that underlies general relativity, into more exotic mathematical structures. One of these is Finsler geometry, a generalization of Riemannian geometry in which the distance between 2 points depends not just on their positions but on the direction of travel between them. In Riemannian geometry, the metric is the same in all directions at any given point. In Finsler geometry, the metric is direction-dependent. The space has a built-in anisotropy, a preferred directionality, that is absent from the smooth, isotropic spaces of standard general relativity. Embedding wormhole solutions in Finsler-like frameworks changes their properties in ways that are subtle but physically interesting. The throat of a Finsler wormhole is not geometrically equivalent in all directions. The experience of traversal depends on the direction of motion through the throat in a way that has no analog in standard wormhole geometries. This anisotropy can affect stability, the behavior of tidal forces, and the way quantum fields propagate through the interior. It also connects naturally to theories in which Lorentz invariance is broken. The direction dependence of Finsler geometry is a natural mathematical home for physics that distinguishes between different directions in spacetime. The departure from standard general relativity goes further when you consider what happens to the laws of gravity themselves across a wormhole. In most wormhole solutions studied within a single theoretical framework, the laws of physics are the same on both sides of the throat. The same gravitational constant, the same field equations, the same relationship between matter and geometry. But there is no fundamental reason why this must be so. A wormhole connecting two different regions of the universe, or two different universes entirely, need not connect regions where the physical laws are identical. In certain theoretical frameworks, particularly those arising from string theory and the landscape of possible vacuum states, different regions of spacetime can have different effective laws of physics, different values of fundamental constants, different numbers of light particle species, different strengths of the fundamental forces. A wormhole connecting two such regions would have different gravity laws on each side of its throat. An observer traversing it would pass from one set of physical laws to another, emerging into a universe that looks fundamentally different not just in its contents but in its rules. This is not merely exotic speculation. The string theory landscape explicitly predicts the existence of an enormous number of possible vacuum states, each with its own effective physics, and the question of how these vacua are connected, whether tunneling between them is possible, whether wormhole-like structures could link them, is a serious one in the study of the multiverse. Which brings us to the possibility of wormholes as bridges between entirely separate universes. The maximally extended Schwarzschild solution, the full mathematical description of a non-rotating black hole that first revealed the Einstein-Rosen bridge, contains two asymptotically flat regions, two separate exteriors that are mathematically part of the same solution but are causally disconnected from each other in the classical geometry. They cannot communicate. They cannot exchange signals. They are linked by the wormhole interior, but the interior collapses too quickly for anything to traverse it and carry information from one side to the other. In more general solutions, charged black holes, rotating black holes, and solutions with exotic matter supporting the throat, these two exterior regions can persist, and in some cases, the wormhole between them can be traversable. The result is a geometric structure that genuinely connects two separate, causally disconnected universes, not two distant regions of the same spacetime, but two entirely independent spacetimes joined at the throat. Whether these other universes are real in any physical sense, whether the multiverse implied by such solutions is something the universe actually contains or merely something the mathematics permits, is a philosophical question as much as a physical one. But the geometry is unambiguous. The solutions exist. The bridge is there in the equations. And traversing it would mean not traveling to a distant part of our universe but leaving our universe entirely, emerging into a spacetime that may have its own history, its own physical laws, and no causal connection to anything in the cosmos we know. The idea of hidden wormholes, passages that are not visible from outside, concealed within the structure of spacetime, takes on a particularly vivid form when considered in the context of false vacuum bubbles. The vacuum of space is not necessarily the lowest possible energy state of the universe's quantum fields. Physicists distinguish between a true vacuum, the actual minimum energy state, and false vacua, local energy minima that are stable against small perturbations but can tunnel, through quantum processes, into the true vacuum or into other false vacua. Our universe may inhabit a false vacuum. If so, there exists, in principle, a lower energy state into which regions of our universe could spontaneously tunnel, forming expanding bubbles of true vacuum, or of a different false vacuum, within the fabric of our spacetime. These phase transition bubbles are relevant to wormholes because the geometry at the boundary of such a bubble, the domain wall between the old vacuum and the new, can, in certain conditions, support a wormhole-like structure. A wormhole can hide behind a false vacuum bubble, shielded from outside observers by the domain wall, accessible only to anything that has crossed the phase boundary. The bubble wall acts as a concealment, a geometric screen that hides the wormhole from the outside universe while preserving the passage within. This possibility adds another layer to the question of how you would find a wormhole in the real universe. Not only might it be indistinguishable from a black hole at a distance, not only might it carry no announcement of its presence, it might be actively hidden behind a region of spacetime that looks, from the outside, like a simple bubble of different vacuum energy. There's a related and even more striking possibility. A wormhole, in certain solutions, does not merely connect two regions of a larger universe. It constitutes a universe in its own right. Some wormhole solutions contain what are called multiple asymptotic regions, not just two exterior spacetimes, but many. The complete, maximally extended solution can have an intricate topology with numerous separate asymptotic regions, each of which is, from its own interior perspective, an infinite, open spacetime extending in all directions. From within any one of these regions, the wormhole does not appear as an object in space. It appears as a feature of the cosmos, a structure that, when examined closely, reveals connections to other spacetimes rather than simply to other regions of the same one. In the most extreme versions of this picture, a wormhole is not an object inside a universe. It is a universe, or rather, a structure from which universes grow outward in multiple directions, each asymptotic region a separate spacetime, all connected through the shared interior of the wormhole geometry. The wormhole becomes less like a tunnel and more like a hub. A central geometric structure from which multiple universes radiate. The picture of a wormhole is a toy universe, a small, self-contained spacetime with its own interior structure and its own set of asymptotic regions, is not just a conceptual indulgence. It is one of the most valuable things about wormholes as theoretical tools, because it means that studying wormhole physics is studying cosmology in miniature. All of the deep questions about the relationship between quantum mechanics and gravity that apply to the universe as a whole apply, in a more mathematically tractable form, to the wormhole. And in this laboratory setting, those questions become accessible in ways that the full complexity of cosmology does not easily allow. This is why wormholes have become such a central object in the modern study of quantum gravity. Quantum gravity, the as-yet incomplete theory that reconciles quantum mechanics with general relativity, is extraordinarily difficult to study directly. The regime where quantum gravitational effects are dominant is the Planck scale, far beyond the reach of any experiment. The full equations of quantum gravity, in whatever form they ultimately take, are extraordinarily complex. Direct calculations are typically intractable. But the interior of a wormhole provides a probe. A place where quantum gravitational effects are concentrated, where the geometry is simple enough to be tractable, and where the questions of quantum gravity appear in their sharpest and most calculable form. Studying the interior of a wormhole, how it behaves under quantum perturbations, how information is processed within it, how its geometry responds to changes in the quantum state at its boundaries, provides a window into quantum gravity that the full complexity of the cosmos does not offer. One of the most specific things that wormhole physics probes is what physicists call the factorization problem in quantum gravity. In ordinary quantum mechanics applied to well-separated systems, the quantum state of a system made of two non-interacting parts factorizes. It can be written as a product of a state for each part, with no entanglement between them. But in quantum gravity, with its holographic structure and its connections between geometry and entanglement, this factorization can break down. Two apparently separate regions of spacetime, described by apparently separate quantum systems, can have correlations, entanglement, that prevent the total state from factorizing. Wormholes are precisely the geometric structures that generate these correlations. A wormhole connecting two regions creates entanglement between them, entanglement that is encoded in the geometric connection of the interior. Studying wormhole solutions allows physicists to understand when and how factorization fails in quantum gravity, what the conditions are under which two separate regions of spacetime are truly independent, and when they are secretly correlated through a geometric bridge. This bears directly on the black hole information paradox and its resolution. The information paradox asks what happens to the quantum information encoded in matter that falls into a black hole. As the black hole evaporates through Hawking radiation, the information must, by unitarity, be preserved. It must eventually emerge in the radiation. But how? The geometry of the black hole, in the classical description, does not provide a mechanism for information to escape from behind the horizon. Wormhole solutions provide part of the answer. Recent work, building on the replica wormhole technique, has shown that when you correctly sum over all possible spacetime geometries in the quantum gravitational path integral, including wormhole-like configurations that connect different copies of the spacetime, the resulting calculation of the Hawking radiation entropy follows a pattern called the Page curve. The Page curve is precisely what unitarity demands. The entropy of the radiation initially increases as the black hole evaporates, then turns around and decreases as information begins to emerge, eventually reaching zero when the black hole is completely evaporated and all information has been returned to the radiation. The wormhole geometries in the sum are not exotic additions to the calculation. They are required by the mathematics. The path integral over spacetime geometries naturally includes them, and without them, the page curve does not emerge. The information is returned to the radiation precisely because the sum over geometries includes wormhole-like saddle points that create correlations between early and late radiation, encoding the information in the entanglement between distant parts of the quantum state. This is perhaps the most concrete and technically significant contribution that wormhole physics has made to fundamental physics. Not as a speculative structure or a thought experiment, but as a necessary ingredient in a calculation that resolves one of the deepest paradoxes in physics. The wormhole is not incidental to the solution of the information paradox. It is the solution. And finally, returning to the holographic picture, the interior of the wormhole serves as a five-dimensional laboratory for studying shortcuts, not just geometric shortcuts through space, but conceptual shortcuts through the complexity of quantum gravity. In the ADS/CFT framework, calculations that are extremely difficult in the five-dimensional bulk gravitational theory can sometimes be mapped onto much more tractable calculations in the four-dimensional boundary quantum field theory, and vice versa. The wormhole interior, living in the five-dimensional bulk, is a space where gravitational physics happens in its full generality. But by using the holographic duality, physicists can translate questions about the wormhole interior into questions about the boundary quantum field theory, questions about entanglement, complexity, and quantum information that can be studied with the tools of quantum information theory rather than the tools of quantum gravity. The five-dimensional wormhole interior is, in this sense, a shortcut laboratory. A place where the hardest problems in quantum gravity become tractable, where the geometry of spacetime becomes a calculable function of quantum information, and where the deepest features of the relationship between space, time, and quantum mechanics are laid open for examination. What wormholes teach us about reality is not a single lesson but a convergence of many. They teach us that space is not simply a container but a structure built from something deeper. That geometry and quantum information are not separate subjects but two languages describing the same underlying physics. That the interior of the most exotic geometric structures in the universe is encoded in the entanglement of quantum systems at their boundaries. That the laws of gravity, information, and quantum mechanics are woven together in ways that the classical picture of spacetime never hinted at. The wormhole began as an unusual shape in the equations. It has become a lens through which the entire architecture of physical reality comes slowly, quietly, into focus. There is a quality to the wormhole's interior that resists every attempt to simplify it. Physicists working with wormhole solutions have discovered, repeatedly and in different contexts, that the interior cannot be approximated as a simple pipe. Not a tube, not a corridor, not any kind of hollow passage with uniform properties along its length. Every time a simplified model is used, every time the throat is treated as a featureless channel connecting two endpoints, the approximation breaks down in ways that matter. The interior insists on its own complexity. It carries structure that a flat pipe cannot hold. Part of that structure is topological charge. Topology, as we have seen, is the study of properties that remain unchanged under continuous deformation. topological charge is a quantity associated with a field or geometric configuration that cannot be removed by any smooth, continuous change. It is a knot that cannot be untied without tearing. Certain wormhole interiors encode topological charge in their geometry, a permanent, indelible feature of the spacetime structure that persists regardless of how the geometry is perturbed or evolved. This charge is not a physical charge in the sense of electric or color charge. It is a geometric charge, a signature of the topology of the interior, and it makes the wormhole qualitatively different from any simply connected region of spacetime in a way that cannot be smoothed away. The presence of topological charge in the interior has consequences for how the wormhole interacts with fields threaded through it. Particles with certain quantum numbers can be affected by the topological structure of the spacetime they move through, even if they never come close to any region of extreme curvature. The topology acts at a distance, in a sense, shaping the quantum mechanics of fields throughout the interior by virtue of what the geometry fundamentally is, not merely by virtue of local curvature effects. This makes wormholes powerful testbeds for cosmic censorship. Cosmic censorship, the conjecture that singularities are always hidden behind horizons, never exposed to the outside universe, is one of the central and proven ideas in classical general relativity. It has resisted both proof and disproof for decades. Finding configurations in which it holds, and finding the precise conditions under which it might fail, is one of the most active areas of research in mathematical relativity. Wormhole interiors are ideal laboratories for this investigation, because they can be constructed to approach and probe the boundary of cosmic censorship in controlled ways. A wormhole interior can be designed, through the choice of metric, matter content, and topology, to come close to the conditions where a naked singularity might form, allowing physicists to study what happens at that boundary without fully crossing it. The interior becomes a testbed, a place where the conjecture is stress-tested against the full complexity of the geometry without the need to solve the problem in full generality. And related to this is one of the most elegant features that can be designed into a wormhole, the complete absence of singularities. In standard general relativity, singularities are essentially unavoidable in certain classes of spacetime. The Penrose-Hawking singularity theorems prove that under conditions satisfied by realistic matter and initial data, geodesics, the paths followed by light and matter, must be incomplete. They reach a point beyond which they cannot be extended. This is a singularity, a boundary of spacetime where the geometry breaks down and the equations cease to apply. Black holes have singularities. The Big Bang is a singularity. Collapsed matter forms singularities. Singularities, in classical general relativity, are a feature of the universe rather than an exception. But horizon-free wormholes, wormholes constructed without event horizons, can, in principle, be free of classical singularities entirely. Because they do not possess the one-way causal structure of a black hole, because the geometry does not contain a region from which escape is impossible, the conditions of the singularity theorems are not satisfied. Light rays can pass through the throat and continue. Geodesics remain complete. The geometry extends indefinitely in both directions along every path through the interior. A traversable, horizon-free wormhole is, in this sense, a singularity-free spacetime. A region of extreme curvature that nevertheless avoids the breakdown of the equations. A place where the geometry is wild and complex but remains, throughout, mathematically well-defined. This is not a trivial achievement. Singularities represent the failure of classical general relativity, the places where the theory breaks down and admits that it cannot describe what happens next. A wormhole that avoids singularities by construction is a spacetime in which the classical theory remains valid everywhere, a smooth and complete geometry that stretches indefinitely without tearing. It is as though the wormhole has found a way to be as extreme as physics allows without reaching the point of breakage. And yet, for all of this mathematical richness, for all the elegance of singularity-free geometries and topological charges and quantum information encoding, the wormhole has never been observed. Not once, anywhere, in any form. No telescope has detected one. No gravitational wave observatory has found a signal that unambiguously requires a wormhole rather than a black hole for its explanation. No particle accelerator has produced evidence of microscopic wormholes in quantum foam. No astronomical survey has found a lensing signature that demands the interpretation of a wormhole over any other compact object. The wormhole exists, at present, entirely within the mathematics. It is one of the most precisely described objects in theoretical physics, its geometry worked out in extraordinary detail, its quantum properties explored with increasing sophistication, its connections to fundamental physics established across dozens of subfields. And yet it remains, observationally, a ghost. A structure so well understood in theory and so completely invisible in practice that the gap between the two feels, at times, like one of the most honest admissions in all of science. We know exactly what it is. We have no idea if it exists. This gap is not merely a practical limitation of current technology. It points to something deeper, a genuine uncertainty about whether the wormhole, as a physical object, is something the universe actually contains, or something that the mathematics permits but reality declines to produce. The possibility must be held seriously that the wormhole interior, for all the detail with which it can be described, may not exist as a physical tunnel at all. Not in the sense that the mathematics is wrong, but in the sense that the mathematical solutions describing wormholes may be features of the equations that have no counterpart in the physical world, the way that negative probabilities can appear in intermediate steps of quantum mechanical calculations without corresponding to anything physically realizable. The solutions are real. The question is whether they are solutions to the equations that actually govern our universe, in configurations that our universe actually produces. General relativity is a classical theory, and its solutions include many things: closed time-like curves, naked singularities, traversable wormholes, that may be systematically excluded by the quantum mechanics that underlies it. The classical solutions may be, in this sense, too permissive. They allow things that a fully quantum treatment would forbid. This connects to what may be the most important message that wormhole physics carries for fundamental physics as a whole. Wormholes may be signals of incompleteness. Not incompleteness in the sense of failure, but incompleteness in the sense of pointing beyond. Every place where wormhole physics runs into difficulty, the need for exotic matter, the quantum instability of the throat, the information paradox, the factorization problem, the breakdown of the smooth geometry at the Planck scale, is a place where general relativity and quantum mechanics are in tension, where the two theories pull in different directions and produce inconsistencies that neither can resolve on its own. Wormholes concentrate these tensions. They are geometric structures that exist precisely at the boundary of what the two theories, taken separately, can describe. The fact that wormholes require exotic matter is a statement that quantum field theory and general relativity, taken together, produce configurations that may not be physically realizable. The fact that wormhole throats are quantum mechanically unstable is a statement that the semi-classical approximation, treating the geometry classically while treating the matter quantum mechanically, breaks down in the most dramatic way at the throat. The fact that the wormhole interior encodes the resolution of the information paradox is a statement that a correct accounting of the interior requires the full machinery of quantum gravity, not just one or the other of its constituent theories. Every difficulty with wormholes is a difficulty with the absence of a complete theory of quantum gravity. They are not obstacles to be overcome within the existing framework. They are markers pointing toward the framework that is needed. A completed theory of quantum gravity, a theory that correctly and consistently describes spacetime at all scales, from the cosmological to the Planck, would tell us whether wormholes are real. It would tell us whether the exotic matter they require can be produced by quantum processes, or whether some mechanism prevents them from forming. It would tell us whether the Hawking-like radiation at the throat truly destroys the geometry, or whether quantum corrections stabilize it. It would tell us whether the information-theoretic wormholes of the holographic framework correspond to any physical structure in actual spacetime, or whether they are features of the duality that have no direct geometric meaning. Until that theory exists, the wormhole occupies a peculiar position in physics. Too mathematically precise to be dismissed. Too observationally absent to be confirmed. Too deeply connected to fundamental questions to be set aside. There is a word for structures like this, held between mathematical certainty and physical mystery. The word is threshold. A place that is fully known on one side and entirely open on the other. Where does the wormhole lead? The honest answer, after everything that has been said, after all the geometry and quantum information and holographic duality and modified gravity and quantum foam and entanglement and complexity, is that we do not know. The destination remains unknown. Not unknown in the way that a location on a map is unknown before you look it up. Unknown in a deeper sense. Unknown in the way that the answer to a question is unknown when the question itself has not yet been fully formed. The mathematics can describe the interior in extraordinary detail. It can tell you how tidal forces vary along the throat, how the redshift function shapes the passage, how the quantum complexity grows over time in the geometry of the bridge. It can tell you that the interior lives in 5 dimensions and encodes entanglement and avoids singularities and connects to other universes or to other regions of this one. But it cannot tell you where you end up. Because the answer to that question depends on the physical wormhole, the real one, if it exists, embedded in the actual universe, with its specific exotic matter distribution and its specific quantum state and its specific relationship to the spacetime around it. And that physical wormhole has never been found. so the destination remains open. Not as a failure of the theory, but as an invitation. The universe is not obligated to reveal all of its structure at once. It has been revealing the nature of spacetime gradually, over centuries, in responses to questions asked carefully enough and instruments built precisely enough to receive the answer. The wormhole is the question we are still in the middle of asking, the part of the inquiry where the mathematics has run far ahead of the observation, where theory has built a structure so elaborate and so beautiful that the universe, in its own time, seems almost compelled to either confirm it or explain, with equal elegance, why not? Either way, the answer will tell us something profound. Either there are passages woven into the fabric of the cosmos, connecting distant places and times through geometry richer than anything we can directly perceive, structures built from entanglement and held open by the deep symmetries of quantum gravity, threading the hidden bulk of higher dimensions, encoding the resolutions to the deepest paradoxes in physics. Or there are not. And the reasons they cannot exist will be, in themselves, a map of what the universe is allowed to be. A statement about the laws of physics so precise and so complete that it will have required the full machinery of a unified theory of quantum gravity to write. The wormhole does not promise arrival. It promises understanding. And in a universe as deep and as quietly strange as this one, that is more than enough to keep looking.